let's see how to perform a goodness of fit test, which means the mostly used chi-square test using R. And we also discuss about the alternative non-parametric test for chi-square test as well. First, let's see uh, perform the chi-square test for two samples. Here we use gender and price variables in our data set. You know, gender is a qualitative variable, price is a quantitative variable. Since we are not seeing the data set recently, we can get the summary of the price here, or we can get the summary of the data set first. So I'm using this price and gender to test the independence of price and gender variables. First, we have categorized this price according to the median. So I categorize this price variable because it is a quantitative variable. Above the median is equal to 1, below the median is equal to 0. So I'm recreating price using this command. So this is the empty vector for store the result, and here this for loop goes through each and every data in the price variable and transform that price variable into 0 and 1 of the discrete for a discrete variable. So here if the median of price is 18,800, so if it is equal or less than 18,800, we record the data observation as 0, otherwise it is 1. So let's run this, and now my price newly built price variable has zeros and 1, so I'm considering it as a factor variable. And you can see the table of price and gender now in the obs. So I can access that table by highlighting obs, and this is it. This is price 0 and 1. This is gender 0 and 1. So gender 1 means male, gender 0 is female, and this is the observed frequency table. And we can do the chi-square test by giving the variables in 2 times like this, price and gender in 2 times, and press this. So you can see the output for the chi-square test for independence. The null hypothesis data are independent, so we can't reject the null hypothesis at 5% level of significance since the p-value is greater than 0.05. So price and gender are independent. Or you can give the table output directly to the chi-square test. So we store the table in obs. Now we are calling obs for the chi-square test like this. So it also gives this output. So we can extract the output values using this technique. So you have to store the chi-square test result in a object, and you can access that value. Suppose I am storing the chi-square test result in CHT, and I get the p-value of the test like this. So if you want to calculate the power of the test by using a computational method, which means you have to draw thousands of samples and test the hypothesis for independency and store the p-value in a separate vector, and you can take the decision using that p-value in a separate vector. Uh, so for that purpose, you can access this p-value like this. And suppose you need to get the expected values. So we saw this is the observed frequency table. We can take the expected frequency table by accessing the expected objective object name in the CST output. So these are the expected frequencies. And when we want to use an alternative for chi-square test, we have to go for Fisher's exact probability test. So chi-square test has few assumptions, which means the observed frequencies should be greater than 5 for at least 80% of the sets. So otherwise, the results of the chi-square test is not reliable. And also expected frequency should be greater than 5. So here it is okay, but suppose we didn't met or didn't meet that assumption, so we can use Fisher's test. So you can give the table output directly or give the two variables as we did in chi-square test. So here also it says that the proportions are not equal. So here true odds ratio is not equal to 0. So this odds ratio is calculated using the proportions. So the same test can be performed. So if this odds ratio is equal to 1, which means those two variables are independent. Since the p-value is greater than the significance value, so we can't reject the null, which means these two variables are independent. Let's see at last. Suppose we need to perform or we need to fit a goodness of fit test for one sample, which means you have a result of an experiment rolling a die for 60 times. A die for 60 times, and these are the outputs or the frequencies of this is the frequency of 1, 2, 3, 4, 5, and 6. So we can directly check whether this die is unbiased. So the null hypothesis is expected frequency is equal to observed frequencies, which means the goodness of fit. So since the unbiased die has equal probabilities of occurring each number, so we can directly use chi-square test with the result vector. So which means for each number we have 1 over 6 probability to occur. So then here at 10% level of significance, we can reject the null hypothesis. Since this is 0.07, we can say this die is not unbiased, or this die is biased at this 10% level of significance according to this result. And suppose the die is biased as the probability of 2 is as twice as the rest, which means obtaining 2 has a probability which is twice as obtaining a number other than 2. So then using the distribution theory, we can create the PMF like this. So having 2, the probability of observing 2 is 2 over 7. And the probability of observing another number is 1 over 7. So the summation of these 6 probabilities is equal to 1. Now we can see whether this data is coming from this die. So what you have to do is give the results, which means give the observed frequencies, then gives the argument p, the PMF of the out or random variable, which means if we create a random variable regarding the rolling this unbiased die, so then the PMF is this. So you can give that PMF and check whether this result is coming from the distribution of this. Let's see. And it is given that the p-value is 0.98, which means we can't reject the null hypothesis, which means the expected frequencies are equal to the observed frequencies, which means this data is coming from this die, which means it is an biased die uh, with the probability of having 2 is as twice as probability having a number rather than or other than 2. So this is how you can use chi-square test for one sample goodness of fit and two sample independence case. And if the assumptions are not met, you can use Fisher's exact probability test like this.